In this video, we're going to learn about some new identities. We have a good understanding of how identities work, what we can use them for, but we only have a limited list of identities we've worked with so far. So now we're going to learn how to work with a couple more identities. And this specifically is going to talk about the sum and difference identities. Also, we're going to talk about something called the cofunction identities. One important thing is that with these identities, we're going to be working with multiple variables inside of our identity as opposed to a single variable. So in this case, the variable represents an angle, so really multiple angles. A really important idea to get across here so that you don't make a very common mistake is to understand how our functions work. Cosine of theta. This is how we read it. We read it cosine of theta. This is not cosine times theta. When I do this, cosine theta or sine theta, this is the cosine of theta, not cosine times theta. Theta is inside the cosine function, and we're taking the cosine of this angle. This is not cosine times theta. So anything you think of when it comes to multiplication, like the distributive property or anything else, does not apply to this. And that's a very common mistake. So what we want to do here is, if we're talking about these sum and difference identities, and we look at, say, cosine first, the idea is we're trying to do this. We're trying to take the cosine of a sum. So the cosine of alpha plus beta, where, say, alpha and beta are two different angles, and this is where we have our multiple variables here. So if I'm trying to take the cosine of alpha plus beta, since this is not multiplication, what you cannot do is think about this like it's the distributive property and say the answer is cosine of alpha plus cosine of beta. You cannot do this. These are not equal because this is not multiplication. This is the cosine of this sum. If you could do this, a lot of things with trigonometry would probably be a heck of a lot easier, but you can't. However, if you wanted to take the cosine of alpha plus beta, there is a way to do it without doing this. And this is the way you would do it. You would take the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So it's far more complicated than what you might think of as how the distributive property would work here. And it's not the distributive property because it's not multiplication. Couple of things here is that I'm adding these two things together inside the cosine, but this whole thing turns into a difference. There's also one for the difference formula. If I'm subtracting two things inside my cosine, then the whole thing turns into a sum. And the idea is I'm going to take the cosine of each angle, multiply those together, take the sine of each angle, multiply those together, take the difference or the sum depending on what I started with. Now what you're doing is essentially pulling this thing apart and looking at the individual angles that are going to be added together and taking the cosine of and the sine of those individual angles, and somehow that's going to give you this cosine of the sum of those two angles. Now this can be useful for multiple reasons. It can be useful to work with some basic identities and simplify some expressions like we've done a lot of in the past. We can use it to help us create new identities. We could also use it to find values of angles that we couldn't find before without a calculator. So something like 105 degrees. 105 degrees is not one of our special angles. It's not 30, it's not 45, it's not 60, it's not a multiple of those things. So to this point, if I wanted to find the cosine of 105 degrees, I would have to use my calculator. And I would get some rounded answer. I would get some decimal that's 10 digits long, and I'd round it, and then it would give me an estimate for what the answer is. But now that we know these sum identities, we can find the exact value of this angle, even though it's not a special angle. If I want to take the cosine of 105 degrees, I have to find two special angles that either add together or subtract together to give me 105 degrees, which I can do. If I look at a cosine of 105 degrees, well, 105 is the same thing as 45 degrees plus 60 degrees. 45 and 60 are special angles. So if I break 105 into 45 degrees and 60 degrees and the sum of those two things, I can use this sum identity. In that case, this would be my alpha and this would be my beta. And it really doesn't matter which one you call alpha and beta, because it's a sum and orders and sums don't matter, it's commutative. So I take the cosine of 45 degrees times the cosine of 60 degrees plus or minus the sine of 45 degrees sine of 60 degrees. So if I bring it over here, cosine of 45 degrees is square root of 2 over 2. Cosine of 60 degrees is a half. Minus the sine of 45 degrees is square root of 2 over 2. The sine of 60 degrees is square root of 3 over 2. I do some simplifying. I can say that this is square root of 2 over 4 minus square root of 6 over 4. I can write the answer as square root of 2 minus square root of 6 all over 4. I could also look at it as pulling out the square root of 2 over 4. And I can write this as 1 minus the square root of 3. That would be the same exact answer. Whether you write this answer doesn't matter. I'd say probably you see this more often than this. But this is the exact value of the cosine of 105 degrees. So we don't need a calculator to find some of these angles now. Now this doesn't work all the time. This would only work if you can take this angle and break it apart as the sum or the difference of special angles. Angles we already know how to work with. And if you can, then you can use this identity to find the cosine of angles you couldn't have found before. So let's go with the next one, pi twelfths. So we look at cosine of pi twelfths. Well, it's a little bit harder to do this with radians than it is to do with degrees, because you have to say what two angles, when I add them or subtract them, will get me pi twelfths. And the problem with fractions is you got to worry about common denominators, so it's not the easiest thing to do. But if you look at this, another way you could think about doing this is, let me convert pi twelfths to degrees, and then just do it the way I would do it with degrees, which is much easier. Well, how do you convert to degrees? I'll have to multiply by 180 over pi. The pi's cancel. I get 180 divided by 12, which gives me 15 degrees. So this is really the same thing as the cosine of 15 degrees. Well, what two angles, when I add them or subtract them, and they have to be special angles, would get me 15 degrees? Well, how about 45 degrees minus 30 degrees? So if I think about this as a difference, and I use the difference identity, then I should be able to use the cosine of pi twelfths, or 15 degrees. Which basically tells me that pi twelfths is pi fourths minus pi thirds. Or pi sixths, sorry. Pi sixths. Pi fourths is 45, pi sixths is 30. So this difference, but knowing that this difference is pi twelfths isn't the easiest thing because of the fractions and the common denominator issue. So I think your best bet when it comes to these is to convert to degrees. And then I think when it's in degrees, everyone should be able to see that there are two special angles to add or subtract to give me the answer I'm looking for. So I'm going to say the cosine of 45 degrees times the cosine of 30 degrees plus sine of 45 degrees sine of 30 degrees. Cosine of 45 is square root of 2 over 2. Cosine of 30 is square root of 3 over 2. Sine of 45 square root of 2 over 2. Sine of 30 is 1/2. I get square root of 6 plus square root of 2 over 4, or square root of 2 over 4 times square root of 3 plus 1. Now these answers look similar to the answers we got before, but that's because we're using a lot of the similar angles, and these angles have very similar values to them. So this is how we can use the sum and difference identities to find the cosine of angles we couldn't have found previously. So as far as the identities we just looked at, the sum and difference identities for cosine, there is a proof as to why the identities work the way they do. The proof is a rather elaborate. It has to deal with looking at distances over the unit circle and comparing distances to one another, similar triangles. There's a lot to it. I'm skipping the proof behind the identities in that I really would rather you focus on learning how to use the identities right now, and at a later date we could go and look into the proof behind the identities. Now, the next thing we're going to look at is the cofunction identities. And with these cofunction identities, the reason why we're looking at these is this is sort of how we get the sum and difference identities for the sine function. We use the cosine sum and difference plus the cosine cofunction identities to get the cosine sum and difference identities. But these are identities you should know already. You might not realize you know them, but you do. In that you know what the unit circle looks like, you know the values around the unit circle, and that there's a pattern to those values. And you've also recognized that some functions have very similar names, except for the co part. So we have sine and cosine, secant and cosecant, tangent and cotangent. These names are similar and they just have a co in front. There's a reason for that. If we look at complementary angles, two angles that add up to 90 degrees, and we look at these cofunctions, the idea is that complementary angles have the exact value when it comes to cofunctions. If I looked at the unit circle, and I look at two angles, 60 degrees, 30 degrees. These are complementary angles. They add to give me 90 degrees. This would be 1/2 comma square root of 3 over 2. This would be square root of 3 over 2 comma 1/2. This is the pattern that you've recognized in the unit circle. That the x value here and the y value there are the same, and same thing here. Well, if cosine is equal to the x and sine is equal to the y, then the cosine of 30 is equal to the sine of 60. Meaning the x value here is equal to the y value here. Well, I mean, you know that already. You've seen that already. But what's the relationship? The relationship is these two angles are complementary. And yeah, this works for 30 and 60, but it actually will work for all complementary angles. Two other angles, say 10 degrees and its complement, 80 degrees. The sine of one and the cosine of the other should be equal to one another. And that's what the cofunction identities are all about, is recognizing this pattern with these co-functions. Not just sine and cosine, tangent, cotangent, secant, cosecant. So if I look at two angles that give me 90 degrees, something like this. X and y are complementary. I can write this as 90 degrees minus x equals y. So y can be replaced with 90 minus x. So I can write this as x plus 90 minus x, where this is one angle, this is the complement. So these two things are the complement of one another. So that means the cosine of one should be equal to the sine of the other. Or vice versa. The sine of x equals the cosine of 90 minus x. Because x and 90 minus x, because really y equals this, is the complement to x. Well, this is saying the same thing here, just instead of 90, I'm using the radian equivalent, which is pi halves. So this is, all these identities are written in terms of radians, but you could do them in terms of degrees as well. Now what we can do here is look at finding the exact value of sine of 15 degrees using the cosine sum and difference identities as well as the cofunction identities. So what do we know? We know that sine of 15 degrees is equal to the cosine of its complement. Well, the complement of 15 degrees, what do I add to 15 degrees to get 90? That would be 75. So sine of 15 degrees equals the cosine of 75 degrees. Well, I can find the cosine of 75 degrees because 75 is equal to the cosine of 45 plus 30. And that's a sum. Well, that means I can do the cosine of 45 times the cosine of 30 minus the sine of 45 times the sine of 30, all degrees, gives me the square root of 2 over 2 times, what's it going to be, square root of 3 over 2 minus square root of 2 over 2 times the 1/2. So I end up with square root of 2 over 4 times square root of 3 minus 1. So that is the sine of 15 degrees. So a combination of the cofunction identities as well as the sum of difference identities, I can come up with the sine of 15 degrees. Now here's the thing, you don't want to do that all the time. You can, but you don't want to. What we can do is we can use this to come up with the sum and difference identity for sine instead of using it to find the sum and difference identity for cosine. So here are the sum and difference identities for sine. If I want to take the sine of a sum, I should take the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. This looks somewhat similar to the sum identity for cosine, but there is a major difference. These are different angles I'm multiplying, different functions I'm multiplying, as opposed to cosine and cosine, and also a sum stays a sum. Same thing for a difference stays a difference, but the pattern is very similar. So if I want to find the sine of 75 degrees, I could say that that's equal to the cosine of 15 degrees and then go with that. But rather than go through the cofunction identities and then do the sum or difference identities, I'm just going to go straight with the fact that the sine of 75 degrees equals the sine of 45 degrees plus 30 degrees, and use the sum identity straight for sine rather than trying to go through cosine. So this will be the sine of 45 degrees times the cosine of 30 degrees plus the cosine of 30 degrees sine of 45 degrees. Nope, that's the same thing again. I'm sorry. Erase that. These angles have to switch. This would be 45 degrees. This would be 30 degrees. So I'm taking the sine of 45 and then I'm taking the cosine of 45. I'm taking the cosine of 30, then I'm taking the sine of 30. Alright, so then what do we get? Square root of 2 over 2. Square root of 3 over 2. Square root of 2 over 2. 1 over 2. So I get square root of 6 plus square root of 2 over 4, or I could write this as square root of 2 over 4 times square root of 3 plus 1. And all these answers are looking very similar, and that's because we're using similar angles. These angles have similar values for their answers. You know, it's not always going to happen that way, but for a lot of these it will be. So now I can take the sine of 75 degrees without using my calculator. Now this only works some of the time. You know, think about it. How many different angles can you create using 30, 45, and 60, and you're adding and subtracting them? Well, there's only a couple. I mean, it would be 15 degrees, you would do 75 degrees, you do 105 degrees, and then maybe multiples of those or negatives of those. But other than that, you know, there's not much else you can create using these particular angles, but at least it's something more than what we were doing before. And now we have the sum and difference identities for tangent. Well, if we know that tangent is the sine over the cosine, I could take the sum identity for sine, divide it by the sum identity for cosine, and that'll get me the sum identity for tangent. Rather than go through all that, I'm just going to jump to what the answer would be after you simplified it, and this would be your sum identity for tangent, this would be your difference identity for tangent. These are a little bit trickier in that, you know, simplifying can get kind of complicated. But generally it's the same pattern to what we were doing before. So I go tan 75 degrees. Well, 75 degrees is the same thing as 45 plus 30. Think of this as my alpha and this is my beta, and I plug it into this sum identity here. So I should get the tan of 45 degrees plus the tan of 30 degrees over 1 minus the tan of 45 degrees, tan of 30 degrees. So what do we know here? We know that the tan of 45 is 1. The tan of 30 is square root of 3 over 3. 1 minus 1 times square root of 3 over 3. So I get 1 plus the square root of 3 over 3 over 1 minus the square root of 3 over 3. If you simplify that, I'm going to get 3 plus root 3 over 3 and 3 minus root 3 over 3. These two 3's will cancel, so I get 3 plus root 3 over 3 minus root 3. Normally, we would not have roots in the denominator, so then I'll multiply by the conjugate. Top and bottom. So then I get 3 plus root 3 squared over 9 minus 3, so 3 plus root 3 squared over 6. I could also multiply that out. I could say that this is 9 plus 6 root 3 plus 3 over 6. And what happens here is I'm going to get, let's see where I put this 12 plus 6 root 3 over 6, which would then give me 2 plus root 3. Now that's a lot of simplifying, and I squeezed it in there, I'm sorry, but ultimately I would say, this would probably do it for you whenever you need to use this identity. The only problem is you're looking at your homework in the back of the book. The book's going to write all their answers like this. Also, multiple choice quizzes and tests online. You want to give the simplest answer, so most likely you're going to see this final answer. But in the future, when you're going to actually be applying this in real life terms, this will usually get you where you need to go if you can get that far. But the tricky thing is simplifying, and it's all algebra. I mean, you're rationalizing the denominator, you're finding common denominators. It's going to take you some time to get used to this. But this is the sum and difference identity for tangent. There's also a difference one. A difference one looks a lot like the sum one, just the signs here and here are different than the signs here and here. Alright, so we've seen how we can get answers for particular angles that we really couldn't get before without our calculator. Other things you can do with some of these identities is just simplify particular expressions. So here's something that would say simplify this expression. You're looking at, say, this expression right here. And you would say, okay, how am I going to simplify this? The key is you would have to recognize that this has a pattern similar to one of our identities, in that it's the pattern for the cosine of a difference, where I would take the cosine of alpha, cosine of beta, plus the sine of alpha, sine of beta. And that alpha and beta are 51 and 6. Here, 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 here. If I let alpha be 51 and beta be 6, I would get this exact same thing. So that means that here simplifies into the cosine of 51 degrees minus 6 degrees, which is the same thing as the cosine of 45 degrees, which is square root of 2 over 2. So this whole expression here simplifies to just square root of 2 over 2. Now you can't take the cosine of 51, you can't take the cosine of 6, sine of 51, sine of 6 without your calculator, but you can simplify this whole expression without your calculator into just square root of 2 over 2, because really this whole expression is really just the cosine of 45 degrees. Let me give you another one. So this one, again, you'd have to recognize that there's a pattern to this, and this pattern looks very different, very similar to the pattern for sine of a difference. Alpha minus beta would be the sine of alpha cosine of beta minus the cosine of alpha sine of beta, where alpha and beta are 2 theta and 3 theta. So if that's the case, this is really the same thing as the sine of 2 theta minus 3 theta. That's what this is. 2 theta minus 3 theta is negative theta. Sine is an odd function, so that's the same thing as negative sine of theta. Now we don't know what theta is, so we can't go further than that, but we did simplify this whole expression into just negative sine of theta. This is very similar to things we were working with previously, more so than what we were just talking about a few minutes ago. Alright, here's another one. And this is all just, the purpose of this is just to get you more practice with these identities. So, find the exact value of sine of alpha minus beta, so this difference, given that sine of alpha is negative 3/5, cosine of beta is negative 1/3, alpha is in quadrant 4, beta is in quadrant 3. So, think about, first, what would we do here? If I did the sine of alpha minus beta, I'd have to use the identity that the sine of alpha times the cosine of beta minus the cosine of alpha sine of beta. Now what do we know? We know that this is negative 3/5. We know that this is negative 1/3 given by the problem. We don't know this one or this one. But once we could find these two, we plug them in and that'll get us the answer we're looking for. What do we know? We know also that alpha is in quadrant 4. If alpha is in quadrant 4, the cosine of alpha has to be positive. Cosine's always positive in quadrant 4. And if beta is in quadrant 3, we know that the sine of beta is negative. Now what's the value? Well, that's where we have to use some other things to do this. But once we find those values, we can plug them in and get our answer. Well, let's look. We know that the sine of alpha is negative 3/5. We're trying to find the cosine of alpha. How can we do that? Lots of different ways to do that. We've actually done this type of question numerous times now. So what you're going to do is, I would say probably your best bet is to use the Pythagorean identity. Sine squared plus cosine squared equals 1. So this is negative 3/5 squared plus cosine squared equals 1. Solve for cosine, you got your answer. So cosine of alpha equals the square root of 1 minus 9 over 25. That would be 16 over 25 or 4/5. So here's that one. Now let's look at the next one. We know that the cosine of beta is negative 1/3. We're trying to find the sine of beta. Well, same deal. We know one, we're trying to find the other. We just know cosine. Use the same identity. Sine squared plus cosine squared equals 1. So, sine squared beta equals negative, or plus negative 1/3 squared equals 1. So sine of beta equals negative square root, because it has to be negative, of 1 minus 1/9, or in this case square root of 8 over 3, which I could also simplify to negative 2 root 2 over 3. So this is negative 2 root 2 over 3. Okay, so now that I have all these pieces, now I just have to plug them into this formula and get my answer. So let me get some room here. Alright, so if I use this, I'm going to get negative 3/5 times negative 1/3 minus 4/5 times, this will be a double negative, we already said negative, so sorry. So that's, this negative takes into account that it's negative, so negative 2 root 2 over 3. So I'm going to get 3 over 15 minus plus 8 root 2 over 15, or 3 plus 8 root 2 over 15. So there you go. There's your answer. Keep track of your negatives, keep track of your computation, but the purpose was using multiple identities, not just the sum of difference identities, we can answer this question. Even though we don't know all the things we needed, we could come up with the other pieces using more identities that we already know. The last things we'll go back to here is the verify the identity type question. Make one side turn into the other side. These are a little bit harder now because you have more to work with. You have your reciprocal, you have your quotient, you have your Pythagorean, you have your even odd identities, which we worked with before. Add to that list the sum and difference identities and the cofunction identities, and any one of those things can be used. Now sometimes it's fairly clear what you should use. This right here kind of gives it away. If I want to take one side of this and turn it into the other side, looking at this, I kind of already know I should probably use the difference identity. So I'm going to say that cosine of x times cosine of 90 plus sine of x sine of 90 is what this can boil down to using the difference identity for cosine. Cosine of 90 degrees is 0. So I get cosine of x times 0 plus sine of x times the sine of 90 degrees is 1. So in the long run that just gives me sine of x. But that's not what's on this side. I need to turn this side, which I got into sine x, into the other side. Remember, it's not always going to work out nice, so let me start working on the other side. Cosine x, tangent is sine x over cosine x. These two cancel, and now I just have sine x. And I was able to make one side equal to the other side, thus verifying the identity. But we were using difference identities now instead of some of the other identities we were working with before, and we also threw in a quotient identity into the mix. So now you have to keep building and building your list of identities that you could use in working with these verify the identity questions. Here's another one. Verify this identity. Again, it should be fairly clear how to start these off with some of these, because this right here should kind of give it away. What should you try first? I should try looking at that and using the identity for that, which is a sum identity for sine. So that'd be sine of x cosine of y plus cosine of x sine of y. That whole thing is over sine x cosine y. At least I know I could do that, and then I'd see about, okay, what could I do from there? Maybe I want to mess around with this side. But what I'm going to do is stay on the left-hand side. What I can do is split this fraction apart. So I could say this is the sine of x cosine of y over the sine of x cosine of y plus the cosine of x sine of y over the sine of x cosine of y. Take this denominator and divide each one of these things by that denominator, splitting it apart. These are the same, so that'll give me 1. This is going to be cosine x over sine x times sine y over cosine y, which gives me 1 plus cosine x over sine x is cotangent x. Sine y over cosine y is the tangent of y. These are both using my quotient identities. And that is exactly what I have on this side, thus turning one side into the other. Again, these can get kind of tricky, but sometimes having these identities being so specific to a type of function makes it easier to pick out what identity you should use. When you try something and it doesn't work, remember you can try something again and keep trying different things until you get something to work. When it says verify the identity, you will always be able to turn one side into the other side. It's just how is it done? And keep trying. Just keep trying. These will get easier. You will get better. It takes a lot of time and a lot of practice.